Hello, my name is Ahmed Taha. In this video, I'm going to present Deep Double Descent, where bigger models and more data hurt. This is a heavy paper with many experiments, so I will focus on two key ideas. These are the core contributions of the paper. After presenting these key points, I will present the paper in details. The key takeaways are what is double descent and what is the effective model capacity. If you understand these ideas, the rest of the paper becomes trivial. Before presenting double descent, I will go over the single descent, which is common in classical machine learning literature. In classical ML, we learn about the bias-variance trade-off. In the high bias region, our model is underfitting and more training epochs help. However, if we increase our model capacity, our model is now overfitting and more training epochs hurts. From this classical perspective, we observe a single descent in the generalization error. This happens when our model is underfitting, and we are accordingly advised to keep our model's capacity low to avoid overfitting. The double descent paper offers a different perspective in which we observe not a single descent, but two. Double descent agrees with classical ML about underfitting and overfitting when our models are underparameterized. Yet, as we increase the capacity of our models further and further, our models becomes overparameterized. After a certain threshold, we observe another descent in the test error or the risk. The paper refers to this threshold as interpolation threshold. It is called interpolation threshold because it indicates whether a model has enough capacity to fit the training data or not. For instance, in this slide we have two models. The one on the left-hand side is a simple linear model trained on noisy data, which is the blue dots. This linear model doesn't have enough capacity to interpolate the training data, so this model falls below the interpolation threshold. The fact that a model falls below the interpolation threshold is not a bad thing. In fact, this linear model will have a good generalization performance on the test dataset. The interpolation threshold tells us whether a model can fit the training data and achieve a zero train loss or 100% accuracy on the training dataset or not. Another example is shown on the right-hand side. We have an over-parameterized model above the interpolation threshold because it can memorize the training data and achieve zero train loss on it. Again, the interpolation threshold tells us about the model's performance on the training dataset only, but it tells us nothing about the model performance on the test dataset. The paper shows that this threshold can be moved left and right depending on many factors, but the paper focuses on three factors only. The three factors are the number of parameters, the number of training epochs, the number of training samples. Depending on these factors, our threshold can move left and right. These factors can either hurt or help our model in terms of generalization error. It is worth noting that the paper doesn't say that these are the only factors. In fact, it is possible that other factors can change the capacity of our model. In this figure, we observe how the number of parameters can either hurt or help our model. The x-axis indicates the number of filters within ARISNet 18. As we move to the right, the number of filters increases and accordingly the number of parameters increases. By increasing the number of parameters, the capacity of our model increases as well. Accordingly, the train error in the dashed line decreases further and further as we increase our model capacity till it reaches zero. The train error makes total sense, but the test error is interesting. As we increase the model capacity, the test error decreases at first and then increases. This follows the classical ML regime and the bias-variance trade-off. Yet something interesting happens when the model capacity reaches a certain threshold. If the model capacity crosses a certain threshold, the test error undergoes a second descent and decreases again till it outperforms the test error within the classical regime region. So this figure illustrates double descent in a nutshell. Later in the presentation, I will dig deeper into this phenomena and show how different factors affect it. But now, I will present another key idea in the paper, which is the effective model capacity. In classical ML regime, we regard the number of parameters as the only factor that controls a model capacity, More parameters means bigger capacity, and that's it. All other factors such as the training data distribution, the architecture of the network, the optimizer, the number of epochs are irrelevant. This changes in the over-parameterized regime. In this regime, the model effective capacity depends on the number of parameters, the architecture, the training dataset, the optimizer, and other hyperparameters as well, for example, the number of epochs. In the paper words, we define the effective model capacity of a training procedure as the maximum number of samples on which it can achieve close to zero training error. The effective model capacity depends not just on the data distribution and the architecture of the classifier, but also on the training procedure, and in particular, increasing training time. This means increasing the number of epochs will increase the model capacity. Concretely, we compute the effective model capacity by training the model on a small number of samples. If it achieves 100% training accuracy after training, we reinitialize and train on a larger set of randomly chosen samples. We iteratively perform this process, incrementally increasing the sample size each time until the model no longer fits all the training samples perfectly. Of course, there are few caveats and technicalities to this approach. For example, the model might achieve 100% accuracy on one subset, but not another subset of a similar size. There is no bulletproof solution to these problems. The double descent papers tries to address these issues whenever possible. Similarly, this follow-up paper tries to address these issues by introducing more changes. For example, sometimes they only train the network till it fit 98% of the training data. My point is that one needs to be careful when trying to replicate these experiments because there are a few technicalities that one needs to be aware of. Now that I have presented the two key ideas in the paper, I shall present all the rest of the experiments and details. First, the paper lists the assumptions made by classical ML statisticians and practitioners. In terms of model, classical statisticians prefer smaller models to avoid overfitting, while practitioners prefer bigger models because they generalize better. In terms of the number of epochs, in classical ML, we prefer smaller epochs, for example, early stopping to avoid overfitting, while practitioners train their models till zero training loss because these generalize better. In terms of data, both classical statisticians and practitioners prefer more data. The paper questions these assumptions. As mentioned previously, the paper defines the effective model capacity as the number of samples that a model can fit. This is not a theoretical metric, but a concrete one. This metric depends on multiple factors, such as the number of parameters, the number of training samples, the type of the architecture, the optimizer, etc. So it's a good practice to think about these questions before moving forward. Let's answer the first question together. Assume we have a toy dataset with 50 samples and a toy ResNet network. Let's say that our model can only fit 25 samples from our toy dataset. In this case, the effective model capacity of our model is 25 samples. Now, what happens when we increase the number of parameters of our model? I hope you see that as we increase the number of parameters, the network can now achieve zero train loss on more than 25 samples, let's say 40 samples. So as we increase the number of parameters, the effective capacity of our model increases. Similar to the number of parameters, I hope it is clear that increasing the number of epochs will also increase the model capacity because the network will have more chance to reach zero train loss. The third question is a bit tricky, that's why I removed the answers, but here is what the paper reports. Let's say that our toy ResNet 18 can fit 25 samples, then its effective capacity is 25. If we increase the number of samples, say to 50 samples, then our original network won't be able to reach zero train loss on the bigger dataset. Instead, we will need a bigger model to be able to fit the new 50 samples. So by increasing the number of samples, our model capacity does not change. It is just that we need a bigger model to fit the bigger dataset. So far, we have been talking about model capacity and the train error. Yet what we really care about is model generalization. Basically, how does double descent will get us better models? We don't care about the train error, but what we really care about is the test error. As we mentioned previously, increasing the number of parameters will mean increasing the model capacity. This means we can achieve zero train error faster. But what about the test error? If we move from the under-parameterized regime to the critical regime, the test error will increase. However, if we move from the critical regime to the over-parameterized regime, the test error will decrease. The main takeaway from this figure is that more parameters can either hurt or help your model. It really depends on which regime is your model. Is your model in the classical regime region or is it in the over-parameterized regime? This figure shows what happens to the test error as we increase the number of epochs. The darker curves indicates more epochs. Similar to the number of parameters, if we increase the number of epochs, we will definitely increase our model capacity, but that doesn't necessarily mean a lower test error. If our model is under-parameterized or over-parameterized, more epochs will means lower test error. However, if our model is in the critical regime around the interpolation threshold, the test error will increase as highlighted by the red arrow. This figure shows what happened to the test error as we increase our training dataset. The cyan curve denotes a small training dataset, while the blue curve denotes a large training dataset. If our model is under-parameterized or over-parameterized, more data will help and we will achieve lower test error. However, if our model is in the critical regime around the interpolation threshold, the test error can increase as highlighted by the red arrow. In this example, adding 4.5 times more samples hurt the test error. In summary, having higher model capacity will always lead to lower train error, as you can see on the figure on the right. The x-axis denotes the number of parameters and the y-axis denotes the number of training epochs. The color scale denotes the train error value. As the number of parameters increases or the number of epochs increases, the train error decreases. However, it's a different story for the test error as shown on the left figure. As the number of parameters increases, the test error decreases first, and then it increases, and then it decreases again. Similarly, if you follow this vertical line, as the number of epoch increases, the error decreases first, and then it increases, and then it decreases again. The paper delivers an informal hypothesis for double descent. Our model lies in the under-parameterized regime when the effective model capacity is sufficiently smaller than n. N is the number of training samples, and our model lies in the over-parameterized regime when the effective model capacity is sufficiently larger than n. And finally, our model lies in the critical regime when the effective model capacity is approximately equal to the number of training samples. The authors admit that this hypothesis is informal because there is no formal specification for the sufficiently smaller and sufficiently larger terms here. The paper shows double descent on multiple architectures. For example, they use the standard ResNet 18. This architecture has 64 filters in the first stage, and then the number of filters doubles from one stage to the next. In this figure, the x-axis controls the number of parameters in ResNet 18 by changing the number of filters in the first stage. For instance, if we set the number of filters to 10 instead of 64, we can still double the filters from one stage to the next. The last point on the x-axis here is basically the formal ResNet 18 architecture. Besides ResNet 18, the paper shows double descent on vanilla CNN architecture without residual connections and the transformer architecture. For CNN, the paper controls the number of parameters by changing the number of filters. For transformers, the paper controls the model capacity by changing the embedding dimension d_model. The paper uses SGD and Adam optimizer in their experiments. Also, the paper evaluates double descent at different noise levels in the dataset. Noise labels are injected by randomly assigning incorrect label to p% of the samples. The paper divides the experiment section into 3 parts. The first part shows double descent when increasing the model size. The second part evaluates double descent when increasing the number of training epochs. The third and the last part shows the effect of dataset size on double descent. These figures show double descent on two datasets, CFAR 100 and CFAR 10. ResNet 18 is used on all experiments, and the x-axis is a proxy for the model size, while the y-axis denotes the train error and the test error. The train error figures here are easy to understand. As we increase the model size, the train error goes to 0. However, the test error figures shows the double descent phenomena. As the model size increases, the test error first decreases, then increases, and then decreases again. This phenomena is visible across datasets and at different levels of label noise. The paper draws attention to a couple of key observations. The first observation is how double descent is more visible on noisy datasets. This is important to highlight because real-world datasets are expected to be noisy, so double descent would be more visible on real-world datasets. The second observation is that the interpolation threshold can be shifted to the left and the right. Remember, the interpolation threshold is where the effective model capacity equals the number of training samples. This is the model size where the test error peaks, as highlighted by the red point here. So what factors shift the interpolation threshold? The first factor that shifts the interpolation threshold is the noise level in the training dataset. By increasing the noise level, we notice how the test error peak shifts to the right. This indicates that the interpolation threshold shifts to the right as well. The second factor that shifts the interpolation threshold is the augmentation level used during training. In these figures on the left, we are not using any augmentation, while on the figures on the right, we are using augmentation. As you can see, by increasing the augmentation level, we shift the interpolation threshold to the right, as you can see here. All previous experiments are done using ResNet 18 and CFAR dataset. In this figure here, the authors show that double descent appears in transformer models trained on text data. To increase the model capacity, the paper controls the embedding dimension, as you can see here on the x-axis. As with ResNet, the train loss decreases steadily as we increase the model capacity, yet the test loss descends first and then increases and then descends again as the model size increases. This is the last experiment in the model-wise double descent section. The next set of experiments study double descent as we increase the number of training epochs. Yet before delving into that, the paper shares an informal intuition for double descent and why does it happen. So let's dig into that. I believe the intuition behind double descent is important to discuss. I'm not going to simply share what the paper claims. I'm going to bring different perspectives from different sources and try to align these together. It's important to note that there is no solid mathematical foundation that explains why double descent happens. In fact, this follow-up paper, A U-Turn on Double Descent, argues against how we count parameters and its relation to double descent. So please take the following slides with a grain of salt. Before discussing the resources in the previous slide, I want to present a hand-wavy intuition for double descent. To do so, I will recap what is a delta function. A delta function is a simple function that has a zero value for the entire domain except for a single value. For instance, this is a delta function that is zero everywhere except when x is equal to a. For simplicity, let's say it has value equal 1 when x equal to a. Now let's say that we are in the classical ML regime. We have a single model that is under-parameterized. These blue dots are our training samples, and the blue curve is our single model that overfits the noise, as you can see in this figure. This model has a limited capacity, and its best case scenario would be to memorize the training data, including the noise, as you can see in this figure. In contrast, if we have an over-parameterized model, this model has enough capacity to act as an ensemble. Again, it is just a single model, but it acts as an ensemble. In other words, the over-parameterized model can be broken down into one model that fits the global structure plus a bunch of other tiny models that fits the noise. In the left-hand side here, there is a single linear model that captures the global structure in the training data. On the right-hand side, there are three tiny models, three delta functions with three different colors. Each one of these tiny models memorize a particular training sample. For instance, the green delta function, when added to the global model, captures the training sample at x equal to 6. So it adds a little bump on that line here, and it contributes 0 everywhere else. Basically, imagine adding these tiny bumps onto the blue model here at x equals 6 and x equals 4 and x equals 8, which help us memorize the training samples by combining the global model on the left-hand side with the tiny models on the right-hand side. Our over-parameterized model acts as an ensemble. This ensemble achieves 0 train loss and overfits the training data, but it's still generalized to the test data. It generalized because these tiny models that overfit the training data are active at a particular values only, exactly 4, 6, 8. On the test dataset, these tiny models contribute nothing while the global model becomes active. The key takeaway from this slide is that an over-parameterized model can act as an ensemble, and it can be broken into a combination of multiple models. Now I'm going to present the same intuition but using the resources I mentioned in the previous slides. For example, I'm using Peter Bartlett slides here. This slide is about benign overfitting. It describes a model f hat as a combination of a simple component useful for prediction and a spiky component useful for benign overfitting. In different words, the simple component f node helps the model generalize on the test distribution, while the spiky delta component helps the model achieve 0 loss on the train dataset. While the word ensemble is not explicitly mentioned in this slide, this equation indicates that a model f hat can be regarded as an ensemble that contains at least 2 simple components, one that generalize and another that memorize. This is another slide from Peter Bartlett where he describes a model as a summation or contributions from multiple kernels. I'm not going to introduce kernel methods in this video, but you can think of this model f hat as an ensemble of kernels. Gaussian kernels are typically used with kernel methods, but not in this slide. In this slide, this singular kernel is used. This kernel, as you can see here, goes to infinity at x equals 0. It remains smooth from -1 to 1, and it is 0 outside that domain. This is not exactly delta functions that I presented previously, but it serves the same purpose. These singular kernels help memorize the training data and achieve 0 loss, yet they don't affect the prediction or generalization of the model on the test distribution. Now I'm going to switch gears to the double descent paper and quote the official presented intuition. So according to the paper, informally, our intuition is that for model sizes at the interpolation threshold, there is effectively only one model that fits the trained data, and this interpolating model is very sensitive to noise in the train set. That is, since the model is just barely able to fit the training data, forcing it to fit even slightly noise or misspecified labels will destroy its global structure and results in a high test error. However, for over-parameterized model, there are many interpolating models that fit the train set, and SGD is able to find one that memorize or absorb the noise while still performing well on the test distribution. To summarize this, an under-parameterized model effectively offers one model that is sensitive to noise. In contrast, an over-parameterized model offers many models, and some of these models are able to absorb the noise. While the paper didn't use the word ensemble explicitly, it indicates that we are working with many interpolating models inside an over-parameterized model. The third resource I'm going to use to present double descent intuition is this paper, a U-turn on double descent, rethinking parameter counting in statistical learning. The paper reconsiders how we count the number of parameters in classical statistical methods such as decision trees and linear regression. I'm going to borrow one section from this paper. I am not sure the authors will like this presentation because they argue that double descent doesn't exist, or at least double descent is just too U-shaped unfolded. In all events, I think this is a good paper. Anyone interested in double descent topic should definitely read it. The paper has many interesting experiments, but I'm going to present the experiment on decision trees only. A decision tree is a famous classical modeling approach. In decision tree, we have a decision node that guides us toward the tree decision. Leaf nodes contain samples from our training data set, and once we reach a leaf node, we check the samples within the node and decide what outcome to make. For instance, if we reached a leaf node and the majority of samples belong to a binary class, let's say 1, then our final decision or outcome will be 1. If you know decision trees, you should know that the number of leaves is maximum the number of training samples in our training dataset. We simply cannot have more leaves than training samples. So the only way to create an over-parameterized model using trees is through random decision forest. Random decision forest is just a fancy word of saying that we are going to use many decision trees, basically an ensemble of trees, and average the decisions of these trees together to reach a final decision through like majority voting or averaging. The key idea here is that in an over-parameterized model, we have an ensemble. By combining these models together, we make a final decision. This figure comes from the U-turn on double descent paper. The figure shows a typical double descent curve. The blue curve shows a classical bias variance trade-off where we only have a single decision tree in our model. As expected, we observe the U-shaped test error curve, but then the red curve shows the impact of using decision forest, which is basically a tree ensemble. By switching to a tree ensemble, our model becomes over-parameterized, and now we observe what seems to be another descent in the test error. So to summarize, our over-parameterized decision tree model is a model ensemble. In this ensemble, there is definitely models that overfit or memorize the training data. Despite that, our test error decreases because while some models absorb the noise and memorize, there are other models that capture the global structure and generalize. The final resource I'm going to cite is an Introduction to Statistical Learning book. I will use an example from section 10.8. In this example, we have a training set of 20 samples. These are the black circles here. The black curve denotes the ground truth. The yellow or orange curve denotes the learned model. This model is learned by solving a least square regression problem using the responses onto a set of 8 basis functions. In simple terms, we are using least square regression to estimate the beta coefficient of this equation here. With 8 basis function, we have 8 beta coefficient to be estimated. As you can see, the learned model delivers a good approximation for the ground truth. Now let's try to increase the degrees of freedom of our model. So instead of 8 degrees of freedom on the left-hand side, the book tries both 20 degrees of freedom and 42 degrees of freedom. With 20 degrees of freedom, the learned orange model delivers a very poor approximation. Surprisingly, when we increase the degree of freedom from 20 to 42, the learned model becomes better. It is not ideal, but significantly better compared to the model with 20 degrees. Now the question becomes why this model with 42 degrees of freedom is better than this model with 20 degrees of freedom. With 42 degrees of freedom, there are an infinite number of solutions that achieve zero train loss. The book chooses the solution with the smallest sum of coefficients beta, where beta are the coefficients of our model. This is known as a minimum norm solution. Now I'm going to break from the book explanation and promote the ensemble perspective. With 42 degrees of freedom, there are many solutions. I believe the key question is, are we selecting a single solution from these many solutions, or are we combining multiple solutions into a global over-parameterized solution? The book claims a single solution, while I'm leaning towards a combination of solutions for the following 2 reasons. The first reason appears in the figure. I noticed that the learned model captures the global structure of the ground truth in general. For example, here, maybe a little bit here, but it has few spikes. Interestingly, these spikes happens very close to the training samples, like here, and this reminds me of the delta functions that I mentioned previously. These delta functions becomes active exactly at the training sample in order to reach a zero train loss, but they have no impact on the prediction and generalization of our model on the test dataset. The second reason I'm leaning towards an ensemble model is the interpretation of the minimum norm solution. According to the book, the minimum norm solution minimizes the squared coefficient. If you look at this term as an L2 regularization, we know that this type of regularization minimizes the values of beta coefficient, but it does not set the beta coefficient exactly to 0. This is a well-known difference between L2 and L1 regularization, which are also known as ridge versus lasso regularization. My point is that given an infinite number of solutions, the learned model will be a combination of one dominant model that captures the global structure plus other models with minimal impact because their beta coefficient is very small, but not exactly 0. These other models help achieve zero train loss, but they have no impact on prediction and generalization of our model on the test dataset.
To wrap up the intuition discussion, it's important to state that as of 2024, there is no solid mathematical understanding for the double descent phenomena. I tried to align the paper's intuition with other resources. In this presentation, I promoted the idea that an over-parameterized model contains many simple models inside it. This idea should feel natural to those familiar with Fourier transform. The over-parameterized model can be regarded as a combination of simple low-frequency terms plus complex high-frequency terms. On top of that, other deep learning papers have promoted the idea that an over-parameterized model contains simpler components. These components are given different names by different authors. Some call them circuits, some call them hypotheses. If my perspective on over-parameterized models turned out to be wrong, that would be my wrong interpretation for the good resources I mentioned in the previous slides. Finally, I want to recommend this paper here to those interested in studying double descent phenomena. As I mentioned previously, the paper argues for a different perspective, so it is worth reading. Now that I'm done with the double descent intuition, let's go back to the experiments. As mentioned previously, double descent can be observed if we increase the model size, the number of training epochs, and the amount of training data. The next set of experiments focus on the epoch-wise double descent. In this figure, we again use ResNet 18 and CFAR dataset. In the left-hand side, we have three different models of three different sizes. The three models are trained for different number of epochs as shown on the x-axis, while the y-axis shows the test error. For the yellow model with small capacity, we observe a single descent as we increase the number of epochs. This aligns with classical ML literature, where a small model won't have enough capacity to memorize the trained dataset and accordingly will generalize better on the test dataset. For the green model with medium capacity, we again observe a single descent, but the test error starts to increase as we increase the number of epochs. This pattern also aligns with classical ML literature, where the model starts to memorize the trained dataset and suffer on the test dataset. Finally, for the red model with the highest capacity, we observe a descent in the error and then an increase and then a second descent. This curve shows that double descent happens not only as we increase the model size, but also as we increase the number of training epochs. In the right-hand side, the figure shows double descent as we change the model capacity on the x-axis and the number of training epochs on the y-axis. The color denotes the loss value. For a small model, we observe a single descent. However, larger model goes through a double descent, like the loss decreases, increases, and then decreases again. The same double descent phenomena is observed on different architectures, ResNet 18 and vanilla CNNs, on different datasets, CFAR10 and CFAR100. As we increase the number of training epochs, the train error decreases smoothly, but it's a different story for the test error. The test error descends, then increases, and then descends again. As with model size double descent, we observe double descent more clearly with noisy datasets. Now it's time to present sample-wise double descent experiments. It is commonly believed by both ML statisticians and practitioners that more data always helps. Yet this paper shows scenarios where more data doesn't improve performance. It might even lower the performance. In this figure, the x-axis denotes the model capacity and the y-axis denotes the test error. We are training different models with different trained dataset sizes here. The beginning and the ending of the curve makes sense. Basically, more data leads to lower test error. That's normal. Yet there is a critical region in the middle of the figure where adding more data doesn't improve performance. In this green region, we increase the training samples by 4 times, yet the performance of the model doesn't change. The paper shows double descent phenomena using different levels of noise in the left figures. In both figures, adding more data doesn't improve performance. Then the paper goes further and shows a scenario where adding more data hurts performance. In this scenario, a small model in orange suffers higher test error as we increase the amount of training data. The large model in blue doesn't suffer like the smaller model, yet the large model performance remains almost unchanged as we increase the training dataset by roughly 2 times before the test error starts to decrease normally as expected. In this figure, the paper measures the train and the test error as a function of both the model capacity and the size of the training dataset. The x-axis denotes the model capacity, while the y-axis denotes the number of samples in our training dataset. The figure highlights 3 model sizes: a small model in orange, an intermediate model in green, and one large model in red. For the small model, the train loss increases as we increase the number of samples due to the limited capacity of the model, but the test error decreases, which is a good thing. For the large model, the train error remains roughly the same since the model capacity is large enough to overfit the training data and generalize on the test dataset. For the intermediate model, which is a surprising case, the train error remains stable for some time and then increases as we increase the training dataset because the model capacity is no longer enough to memorize the training data. And this is clear from this figure here. Surprisingly, for the intermediate model, the test error decreases first and then remains roughly the same despite increasing the number of training samples by almost 4 times. This is an example that more data doesn't always help, and one should take into account the model capacity being used. I want to wrap up this presentation with few final thoughts. First, double descent doesn't happen with early stopping. Second, double descent is observed more strongly with noisy datasets. And a reminder that the effective model capacity depends on the training procedure, including the optimizer, the augmentation, the hyperparameters, the number of training epochs. All of these are taken into account when computing the effective model capacity. Another thing that should be taken into consideration is the data distribution. So for the same model, we can have different effective model capacity on different datasets. To conclude, the model performance on the test error depends on many factors and not just the number of parameters. One should take into account other factors such as the number of training epochs and the number of training samples. Also, the relationship between the model performance and these factors is not straightforward. As shown in this figure, increasing the number of parameters can either hurt or help our model. If we move from an under-parameterized regime to a critical regime, the test error increases. However, if we move from a critical regime to an over-parameterized regime, the test error decreases. So we shouldn't make simple assumptions like adding more data will always help or that more epochs leads to bad overfitting. Things are a bit more complicated than that. Finally, these are the resources that I have used to create this presentation. I'm going to make this presentation public and leave the link in the description of this video. If you are still listening till this point, I want to thank you for your patience and I hope you enjoyed this video.